Hello and welcome to How Cloud Foundry Goes Bang. I'm Toby Lorne, a site reliability engineer at gov.uk PaaS and an occasional Cloud Foundry contributor. Gov.uk PaaS is UK-based web hosting powered by Cloud Foundry, so you can get on delivering your government service without needing specialist infrastructure skills or knowledge of infrastructure as a service providers. We power things like the Department for International Trade's great.gov.uk to help people import and export goods into and from the UK. We power gov.uk Notify, which helps government services send emails, text messages and letters to their users. We power things like simple energy advice, so you, a citizen, can reduce your energy bills and get advice to make your home greener. Or if you recently purchased a drone or model aircraft, you can register to fly it online via the Civil Aviation Authority, who's another gov.uk PaaS user. Gov.uk PaaS have been running open source Cloud Foundry since December 2015. We started out in AWS Ireland, EU West 1, and in May 2018 we added a London region, EU West 2, again in AWS. Gov.uk PaaS is part of the Government Digital Service, and we're hiring right now. We're quite similar to cloud.gov and cloud.gov.au, which are both government PaaSes run by United States and Australia respectively. We have and have had a strong commitment to open source since the start. We published a blog post back in 2015 on why we were choosing Cloud Foundry as our choice for a platform as a service, and we've contributed and made open our code since the get-go. We have over 65 open source repositories, from our PaaS CF repository, which is our CF deployment repository, or CF CLI plugins like Conduit, or open source brokers for AWS RDS, S3, or for Avon.io. Today I'm going to tell you 3 stories: a short story about browsers and complexity, a slightly longer story about abstraction and service discovery in Cloud Foundry, and finally I'm going to recount a large incident that we had earlier this year. First up is a short story about browsers and complexity. When a user signs into Cloud Foundry, they're interacting with a component called a UAA, the User Accounts and Authorization Server. A user is shown a form. They should fill in that form and submit it, probably a username and password, or following the single sign-on journey with an identity provider. UAA will check the cross-site request forgery token and validate the username and password, or the single sign-on token. And if everything is valid, then it will successfully sign the user in. A colleague discovered that when users were signing in using Microsoft Edge, they'd be shown the form, they'd fill it in, and they'd submit it. UAA would always decide that the CSRF token was invalid and the user would not be able to sign in. This is quite odd behaviour, and it was isolated to Microsoft Edge. This is what our UAA looks like. It's slightly customised to fit the gov.uk styling and to be a bit more accessible than the default UAA. And my colleagues posted in Slack, "I think the Crown is stopping Edge users from logging in," and then did some further investigation. This is slightly odd. Why would a Crown SVG stop a user from signing in? This is our reaction. What was happening is the browser was requesting the UAA login page. The UAA login page contains an SVG, which is the Crown, the gov.uk logo. SVGs aren't supported in all browsers, so it's common practice to include a fallback PNG that will be rendered if the browser is unable to render SVGs. You do this by putting an image tag inside the SVG. Usually browsers won't render the image, and they won't request the image specified in the source attribute of the image element. However, Microsoft Edge was always requesting this PNG. Furthermore, we weren't actually hosting the PNG within UAA, we forgot to include it in its assets bundle. The behaviour of UAA, when it's asked for an asset that it doesn't have, is to give you a 302 to the login page. This was followed by the browser, Edge, and when it went to the login page, and this invalidated the CSRF token. Once the user submitted the form, they had submitted the form with an invalid CSRF token. They were no longer able to log in. This is extremely arcane behavior that we couldn't have predicted when we're adding a crown logo to our login page, yet it resulted in quite a few users not being able to log into the platform because of a strange bug. The bug was, unless you have an xlink href attribute that's empty inside the image element inside the SVG, then the Microsoft Edge will always request a fallback PNG, even though it's able to render SVGs. This was fixed in the following pull requests, wherein we specify the xlink href element, and we also host the PNG so it won't respond with a 302 to the login page. The next story we're going to look at is one involving Cloud Foundry's service discovery, and is a story about abstraction. One day, one of our tenants has an incident. They write to us on Slack. We just saw a big spike of HTTP 500 requests. We reply to them, we did a deploy during that time, and we start investigating. They write to us, were you rolling the Diego cells? No, the only VMs that were being deployed were the scheduler VMs. Well, they saw a lot of statsd exceptions when resolving DNS. And this is interesting. We looked at apps.internal DNS request failures across the platform, and we see that there is indeed a spike of failures. But we can also just look at requests generally, and we can see that the DNS request volume suddenly spikes by 4 times. This wasn't correlated with traffic. Why are requests suddenly 4 times higher? We can see in Bosch DNS adapter's source code that there's a naive retry loop, which, if it doesn't get a successful response, it instantly retries without waiting. This retry loop instantly ramps up requests when failures are happening and exacerbates the problem. We can also see TCP listen overflow on the service discovery VM. This occurs when the service discovery controller is not able to respond to incoming requests. It can't accept a new TCP connection. We can see in the logs that there are too many open files. This usually implies that there's a small U limit somewhere which needs to be increased. But let's zoom out a little bit. Why is there HTTP in my DNS? Why do I need to make an HTTP request? Let's look at the lifecycle of an apps.internal DNS request. So when my application makes a DNS request, I will make a request like this, and I'll probably expect an almost immediate DNS response. But what happens is quite different. Any apps.internal DNS requests that Bosch DNS sees are forwarded via HTTP to a component called the Bosch DNS adapter, which also lives on the Diego cell VM. The Bosch DNS adapter needs to look up the app using the service discovery controller. But because this service discovery controller lives on a different VM, it needs to do this securely using mutual TLS. Once the mutual TLS connection has been established, the adapter can make its request and receive a response via HTTP. Because we only deployed 2 scheduler VMs, but we have 3 availability zones, this request could happen across availability zones, further increasing latency inside a single DNS request. Now that Bosch DNS adapter has received its response from the service discovery controller, it can in turn respond to the Bosch DNS request, which will in turn send a DNS response back to the original app. And this was happening approximately 4 times per incoming HTTP request to the tenant's app. The tenant's code was doing this multiple times whenever they were recording a metric. Let's look in version control. Here we can see the developer writing the code is making an assumption that DNS is in fact DNS, locally via UDP. This is not true. In this case, DNS is in fact HTTP via MTLS remotely. We can raise several pull requests. One, ensuring that the platform deploys more than 2 scheduler instances and at least 1 per availability zone. We can also increase the U limit in the service discovery controller, so instead of only being able to service 1,000 concurrent requests, we can service many more. We can also delay Bosch DNS adapter retries and add jitter to avoid a thundering herd problem. And finally, we can work with our tenant so that they cache the IP of their stats DNS client requests, so they aren't making lots of DNS requests within a single HTTP request context. I've detailed a single pull request here that has links to all of the other pull requests. Our last story today is one that's about certificates and persistent environments versus short-lived environments. Earlier this year, we had a major outage of applications hosted on gov.uk PaaS, for which there's a public report on our status page, status.cloud.service.gov.uk. It's been our only P1 incident in 5 years of production and is caused by certificate rotation. You can find a link to the status report on screen now. Before we talk about certificate rotation, we should remind ourselves of what a certificate is and why they're used. There are two kinds of cryptography: symmetric cryptography and asymmetric cryptography. Symmetric cryptography is when the key used for encryption and decryption is the same, and asymmetric cryptography is when there's a public and a private component. The private key is used for decryption operations, but you only need the public key to encrypt something. This means that you can distribute the public key to everyone and keep the private key safe. Everyone can encrypt messages to you, but only you can decrypt the encrypted messages. Likewise, you can use your private key to sign messages. You can distribute the public key, and everyone can use the public key to verify that the messages really were signed by you. A certificate is a public key and some metadata, for instance the common name of the certificate, and all of that is bundled together and signed by a certificate authority known as a CA. As an example, an application or computer will have a certificate authority bundle which contains multiple certificate authority certificates. When you receive a message and an accompanying certificate, you can verify that the message has been signed by the private key relating to that certificate, and you can also check that the certificate has been signed by a certificate authority that you trust. This tells you two things. One, the sender has the private key of the certificate. Two, that the certificate has been signed by a trusted party. These two things together means that you should trust the message. Here we have two components within Cloud Foundry. On the left we've got GoRouter, which is responsible for receiving HTTP requests into Cloud Foundry and routing them to the right application. On the right we have a VM which might represent a Diego cell. There's an application there which has an Envoy sidecar proxy. When the GoRouter receives an HTTP request, it will look up in its route table where it should route the HTTP request to. It will pick a backend destination, and then it will forward that request to the backend. In this case, it picks our Envoy sidecar. It opens a mutual TLS tunnel. It sends the HTTP request down the mutual TLS tunnel. Envoy accepts the HTTP request and forwards it over local HTTP in the network namespace to the application. The application responds to Envoy, which then sends the HTTP response back through the mutual TLS tunnel to GoRouter, which can then reply to the client. In order for this connection to be trusted, GoRouter has a certificate that has been signed by that has been issued by the certificate authority that is trusted by Envoy. And likewise, Envoy has a certificate that has been issued by a certificate authority that GoRouter trusts. Once we get more components in the mix, we can see things become a little bit more complicated. In this example, we show GoRouter, which is able to forward requests to Cloud Controller, UAA, and Diego cells. Cloud Controller additionally has to send messages to UAA. So we see that there's quite a few components that are trusting multiple CAs so that they can validate and trust requests from multiple different components. To use our earlier example of GoRouter and Envoy, this is what happened during our incident. GoRouter was not able to trust Envoy, Envoy was not able to trust GoRouter because the relationship between the CA and the issuing certificate was broken. This was happening between every single component across the platform for which the certificates had been rotated. This was not a particularly good situation to be in. So why did everything break? X509 is the standard which describes how certificates should be formatted, and there are a number of optional extensions to X509, two of which are subject key identifiers, and authority key identifiers. It helps speed up certificate validation and provides an additional guarantee. A common way of generating subject key identifiers is deriving them from the public key, as shown here. Authority key identifiers for certificates should be derived from the subject key identifier of the certificate authority that signs the certificate. Authority key identifiers for certificate authority certificates should be derived from the subject key identifier of the certificate authority. A very common library for cryptographic operations is OpenSSL, and it's used in many Cloud Foundry components. OpenSSL validates certificates if they have an authority key identifier in the following way. If the certificate has an authority key identifier and the issuer, i.e. the CA, has a subject key identifier, then in order for the certificate to be valid, the authority key identifier and the subject key identifier of the CA must have the same ASN1 string representation, otherwise the certificate is invalid. On the left, we see CredHub's behavior for generating certificates, and on the right we see OpenSSL's expectation for how certificates should be generated if they have subject key identifiers and authority key identifiers. CredHub's behavior for generating subject key identifiers for certificates and CA certificates is exactly what OpenSSL expects, but CredHub's behavior for generating the authority key identifier of a certificate is different to what OpenSSL expects. Instead of deriving the authority key identifier from the subject key identifier of the CA certificate, CredHub instead derives the authority key identifier from the public key of the CA certificate. These two different behaviors are equivalent if the function used to generate the subject key and authority key identifiers of the certificate are identical to the function used to derive the subject key identifier of the CA certificate. For example, if we use SHA-1 to generate the subject key identifier of the CA certificate, and we use SHA-1 to derive the authority key identifier of the certificate, then this certificate is valid. But say we used SHA-256 to derive the subject key identifier of the CA, and SHA-1 to derive the authority key identifier of the certificate, then the certificate, when validated against the CA, will not be valid according to OpenSSL. So how did we respond during the incident? Well, understandably, we were quite confused and stressed. We saw that certificate rotation had happened, and eventually, after lots of wrangling with the OpenSSL command line, we observed that certificates had been generated incorrectly. We used our concourse pipelines to generate entirely new key PKI, all the certificates, all the CAs, and we forced a redeployment of the platform. Eventually the platform came back to life. Why did this reach production? Production environments are long-lived, but our development environments are short-lived. We turn off our development environments every night to save money. Our long-lived environments had imported CAs from when the CAs were generated, which predated our use of CredHub. And that means that subject key identifiers were not generated in the way that CredHub generates subject key identifiers. This meant, during rotation, the authority key identifier did not match the subject key identifier of the CAs. When we implemented certificate rotation and CredHub, we tested them using development environments, and then tested certificate rotation using those same development environments that we used to implement CredHub. This meant that they didn't have the CAs with the odd subject key identifiers, which caused the code path to be different. This meant that when production underwent a certificate rotation a few months later, it went kaboom instead of certificates being smoothly rotated. What was the user impact? Our outage began at roughly 5 PM on a working day and affected both of our production regions at roughly the same time. Some apps were able to return to serving traffic at approximately 5 hours later, and we had completely redeployed both platforms at roughly 7 hours later. During this time, end users were unable to access any apps. After we sort of patched ourselves up and got back on our feet, we took some instant action items which we communicated to our users. The first of which was to patch CredHub, or rather update to a patched version. The second was to ensure that our pipeline rotated certificates more often in development and staging so that we would have a better chance of catching future errors. Third was to improve our tests and certificate rotation pipeline output. Fourth was to practice instance more regularly. And the last was to improve the user experience of platform outages. We wanted to improve our certificate rotation tests. Our certificate rotation relies on a maximum hierarchy of 2, that being there can be one CA and then immediately below it leaf nodes. We don't have lots and lots of layers of certificates and certificate authorities. And we now know that it is very important to check that authority key identifiers match the ASN1 string representation of subject key identifiers of certificate authorities. We also made a commitment to practice instance more regularly. We have a commitment to practicing instance more than once per month. We've developed a lightweight Dungeons & Dragons style instant process that our team has called Unlucky Dip. We continue to run slightly more heavyweight game days. Lastly, the end user experience of a platform outage is a bit suboptimal when you just have plain text error messages. So we raised a pull request with thanks to the CF networking team to allow operators to customize error messages so that we can improve and iterate on the user experience of platform outages, either total or partial. So what have we learned in our 3 examples over the last 20 minutes? We first learned that abstractions are leaky, although perhaps we already knew this. Our developer in the service discovery and DNS example assumed that DNS resolution would be quick because it's just a single DNS request over UDP to a local DNS resolver, when in fact the request chain was 2 HTTP requests, including a mutual TLS tunnel that crossed an availability zone. We also learned that distributed systems are hard, both in terms of the auxiliary systems that we have to build to get them to work, for instance service discovery and apps.internal DNS, but also in trying to get them to trust each other, our difficulty with implementing safe certificate rotation, and a huge failure mode and blast radius of when that goes wrong. We also learned in our starting trivial example that browsers are distributed systems. It's quite challenging to work out this isolated failure mode in a single browser that wasn't used by the developers. We had to debug back and forth with the user and eventually download Edge ourselves to verify the hypothesis that it was a fallback PNG. We also learned that certificates are not as simple as they look. Not only do we have to manage a lot of them in a large distributed system like Cloud Foundry, but we're also operating them at machine scale, so we have to make sure that our tooling generates certificates in an appropriate way and in a way that all of the other compatible tooling accepts. This was probably not the consideration that was being made the first time CredHub implemented certificate rotation and generation. And lastly, although we probably also already knew this, the Cloud Foundry open source community is amazing. We wouldn't be able to operate this large platform and serve all of our users across 2 regions with such a small team without standing on the shoulders of some open source giants. So thank you again to the Cloud Foundry community. We also learned, and we definitely already knew this, that network failures happen often. Those are a few ways that Cloud Foundry goes bang. Thanks for watching.